So now we're going to be looking at the energy related to rotational motion. And rotation also has a form of kinetic energy. We call it kinetic energy rotation, and it's equal to 1/2 I omega squared. Okay, so it looks very similar to our linear kinetic energy, 1/2 mv squared. So a baseball pitcher throws the ball into motion where there's a rotation in the forearm about the elbow joint as well as other movements. If the linear velocity of the ball relative to the elbow joint, so v is equal to 20 meters per second, at a distance of 0.48 meters from the moment in the moment of inertia, or the rotational inertia is 0.5, what is the rotational kinetic energy? So here I have to relate what omega is. Omega is equal to v over r, so that's 20 over 0.48. And I get 41.67 radians per second. And so now I can use my formula 1/2 I omega squared. It's 1/2 times 0.5 times 41.67 squared. I get 434 joules. A bus contains a 1,500 kilogram flywheel, a disc that has a 0.6 meter radius. So it's a disc. So formula for disc is 1/2 mr squared. It's just sort of given to you. That I know you don't know this for AP Physics 1. You don't necessarily need to know, but that's what we need to know. The m is equal to the flywheel. The mass of the wheel is 1,500 kilograms, and the r of the wheel is 0.6. So to calculate this I, just to give you a number up front, 1,500 times 0.6 squared, I get 270. 200 kilograms meter squared. So that's the I. Calculate the angular velocity the flywheel must have to contain enough energy to take the bus from rest to a speed of 20 meters per second, assuming 90% of the rotational kinetic energy can be transformed into translational energy. Okay, so what I'm trying to get the bus to is a total kinetic energy of 1/2 mv squared. And that total is 1/2 times 10,000 kilograms times 20 meters per second squared. That's sort of the setup of the problem. How are we going to get up to this speed? Times 20 squared. And that's equal to, 2 times 10 to the 6 joules. Okay. But what they're saying is how much energy needs to be in the flywheel. Assuming that this is only 90% of the energy in the flywheel, which is 1/2 I omega squared. Okay. So if I know I and this, I can solve for omega. So omega is going to be this 2 times 10 to the 6th times 2 divided by 0.9, and then divided by I, which is 270, and then square root this. .3 radians per second. So that's the first part of the question. How high a hill can the bus climb with this stored energy and still have a speed of 3 meters per second at the top of the hill? So if we were to say all this energy in the flywheel, so what's the energy in the flywheel? It was this 2 times, it was just 90% of this. It was 2 times 10 to the 6th divided by 0.9. And that's 2.22 times 10 to the 6 joules. Now, what would it take to take all of this energy, actually, and convert it to energy, potential energy in the... This is kind of a confusing. So at the top of the hill, I'm going to have some potential energy plus some kinetic energy, right? And so I want to figure out how high the hill can be, because I know what the velocity at the top of the hill is, 3 meters per second. So I'm going to set this equal to 2.22 times 10 to the 6th. So I'm going to do 2.22 times 10 to the 6th minus 1/2 mv squared is equal to mgh. And so to find h, I'm going to divide by mg. And so that's 2.22 times 10 to the 6th minus 1/2 times 10,000 times v squared divided by 10,000 times 9.8. Okay. I get 2130 meters. That's what I got, H. Thanks for watching. If you enjoyed this video, I go through a lot more of these exact kinds of problems with much longer videos on my website. It's entirely free. Check out the link in the description below.